Hello everybody, we are going to be covering our Honors Geometry 2.6 notes today. These are the last set of notes for Unit 2, and we're going to be reviewing solving systems of equations in two variables, and we are also going to be learning a new type of geometry today called Taxicab geometry. We don't do a whole lot with Taxicab geometry, but it is kind of cool to see geometry in a slightly different way than what you're used to seeing, and so we're going to introduce Taxicab geometry today. So one of the things that I want to remind you guys of is in algebra, you learned how to solve systems of equations, and systems of equations are really beneficial when you have two equations with two different variables. So far in the class, we've talked about solving single variable equations, like solving for x, solving for t, whatever. But we always run into issues when we have two variables. If we have two variables, we usually have to solve for the first variable and then plug it back in and use the answer from the first variable to solve for the second variable, which is great, but sometimes it's easier if you have a second equation to use to solve for a second variable that you have. So in Algebra 1, you learned a couple different ways to solve systems. You learned how to solve systems using graphing. You also learned how to solve systems using the method of substitution, and then the last way that you learned how to solve a system was through the method of elimination. And elimination is the method that we will use most often. We use it a lot in geometry, and then you'll actually probably use it the most in Algebra 2, unless you are doing matrices, which you don't learn about those till Algebra 2 anyways. But for us, the easiest thing for us to do is actually solve by elimination. And as a reminder, elimination is when you have the same variable with the same coefficient, but one being positive and one being negative. So for example, if I have 5x, I can eliminate 5x by subtracting 5x. Those two things cancel. I could say the same thing as if I have a negative 3x. If I had a positive 3x, those cancel. So my goal with solving by elimination is to have the same variable with the same coefficient in front, but one being positive and one being negative. When you look at this first equation or this first system here, I cannot eliminate my x's or my y's because they just don't eliminate with what we have there. So what I can do is I can actually multiply my first equation by 3. And what that's going to do for me is it's going to allow me to end up with a negative 3y to cancel with the positive 3y that I have in my second equation. So when I multiply that first equation by 3, I'm going to end up with a 12x minus 3y equals 3. And then I can just like gently scribble that out. And that is going to allow me to eliminate my y values. And now I have x values that I can combine, and then I have just numbers that I can combine. So what we're looking at doing here is we are looking at combining like terms, kind of like we would do in like elementary school, where you like add them together and you write the answer below this like weird line that you have. So 2x plus 12x will get me 14x. Drop down your equal sign. Negative 17 plus 3 is a negative 14. From here, I can divide both sides by 14, and you get that x is equal to negative 1. Once you know what x is, you're going to have to plug it back into any of the equations that you see up here to solve for y. You can plug it in here to your new equation that you found. You can plug it in up here to your original second equation, or you can come way up here and plug it into your original first equation. It doesn't really matter. I'm actually going to plug it into the first equation. So we have 4 times negative 1 minus y equals 1. This will be negative 4. Negative 4 minus y equals 1. I'm going to add 4 to both sides. And I get negative y equals 5, which means that y is equal to negative 5. And I just solved the system of equations using elimination. Sometimes you're going to end up with equations where you can't just multiply one of your equations by something. You have to multiply both of your equations by something. And it doesn't matter which variable you choose to get rid of. I actually want to get rid of my x's. So what I'm going to do is whatever the coefficient is for both of those lines, I'm going to multiply the opposite line by the other line's coefficient. What do you mean by that, Ms. Olmsted? I'll tell you. We had a 5. So I'm going to multiply that bottom equation by 5. We had a 6. I'm going to multiply that top equation by 6. And what that does is it automatically makes those two numbers the same. right? Multiply them by each other, they make them the same. However, in order for us to be able to eliminate these variables, you have to have one positive and one negative. I always make the smaller number negative. Why? I don't know, I just do, okay? What we're gonna do is we are going to distribute those numbers into the entire equation and then rewrite them. So that top equation will now be 30x minus 48y equals negative 24. That's my top equation. My bottom equation will be negative 30x plus 25y equals something that I don't know. Let's see, we've got 15, no, we have 14 times 5, and that's going to get me a positive 70, because those are both negative numbers. Now that I'm here, my x's cancel, and what I'm going to do is add my y's together and then add my just numbers together. So 48, that's going to get me a negative 23y. And then 70 minus 24 gets me a positive 46. Sorry if you hear my children in the background. We're going to divide by a negative 23, and we get that y is equal to negative 2. Now, just like with our first equation, in order for us to solve for x, we have to plug that back into one of our 4 equations that we have. And it doesn't matter where you plug it in. I think I'm going to plug this in up here to this equation. It just looks the nicest. I don't know. Again, it doesn't matter. You should get the same answer. We get 6x equals negative 24. When you divide both sides by 6, you get that x is equal to negative 4. And you've just solved the system by elimination. I'm going to go ahead and skip numbers 3 and 4. I'll have those done for the completed notes, but for the sake of this video, I'm just going to go past it. You are going to see a question like number 5 on your test. So you're going to want to make sure that you really pay attention to what's going on here. When you look at number 5, we have parallel lines. This line, and this line are parallel. When you have parallel lines, you have angle pairs. So what we're trying to do is we're trying to figure out what relationship do those two angles in the top and in the bottom half. So like I'm just going to ignore the bottom part of this for now, and I want to look at 3x minus 2y and 120 and figure out what the angle pair is. Since they're both on the same side of the transversal and on the interior of their lines, we have consecutive interior angles. And as a reminder, our consecutive interior angles are going to add to give us 180 degrees. They're the one angle pair other than consecutive exterior angles that are not congruent. They're going to be supplementary. So I'm going to go ahead and add those up together and set them equal to 180. And then the same thing is true for my bottom 2 equations. So I'm going to add those together and set those equal to 180. So I'm going to do that over here. Yeah, I'm going to do it down here. 3x minus 2y. So we have 3x minus 2y plus 120 equals 180. I'm going to subtract 120 from both sides because I want my equations in standard form. So we have 3x minus 2y equals 60. There's one of my equations. And then my second equation, I've got 105 plus 4x minus 3y equals 180. I'm going to subtract 105. And I get 4x minus 3y equals 75. I need to check. I know I probably shouldn't need to check, but I'm going to check anyways because I'm crazy. Oh, that was right, 75. Okay. So these are the 2 equations that I need. So what I'm going to do is I'm going to rewrite them over here as a system. 3x minus 2y equals 60, and then 4x minus 3y equals 75. It doesn't really matter which variables we choose to get rid of. Looking at this, I think I personally want to get rid of the y values. So I'm going to multiply the first equation by 3, the second equation by negative 2. This will get me 9x minus 6y equals 6 times 3 is 180. Negative 8x plus 6y equals negative 150. And then I can eliminate my y's. This leaves me x is equal to 30. So x will be 30. And then I'm going to plug that back into one of my equations. I'm just going to plug it into this top one up here. So 3 times 30 minus 2y equals 60. This is 90 minus 2y equals 60. We're going to subtract 90. We have negative 2y equals negative 30. And we get that y is a positive 15, okay? So as a reminder, you're going to see this one again on your test. It's a pretty highly missed question. And it's highly missed, probably not because you don't know what you're doing, but because this is on a non-calculator portion of your test. So, yeah. Okay. We're going to look at number 6, and then we're going to move on to taxicab geometry. I'm going to help you set up number 6, but we're not going to solve number 6, just again for the sake of time. So it says find x and y so that AB is parallel to DC and AD is parallel to BC. So remember that when you have parallel lines, you should be looking for angle pairs. And because we have a parallelogram, what we have is alternate interior angles, which means that these pink angles are going to be congruent and then the green angles are going to be congruent. So I'll do the pink angles first. We have x plus y equals 2x minus y. We need our x's and our y's on the same side. So I'm just going to go ahead and subtract x and subtract y. There's a 0 on this side. So I've got 0 equals x minus 2y. And then this other one's going to be nice and easy. This is going to be 12 is equal to 3x minus 2y. You're going to use those equations to set up your system to solve. I'll do that in the completed notes, but not right now. Okay, moving on. Taxicab geometry. So the geometry that you have encountered so far in this class is known as Euclidean geometry. And this is named after the father of geometry, who his name was Euclid. If you are like a super math nerd, you should absolutely look into Euclid and all of his postulates and all the fun things that he created and learned and discovered. It was one of my favorite parts of my geometry class in college. It makes me excited, but you know, I'm nerdy like that. However, Euclidean geometry is not the most real world situational geometry. There are other types of geometry out there, but in this class, specifically other than Euclidean geometry, we're going to learn of 2 other geometries. The first one is taxicab geometry, and the second one is spherical geometry. We'll talk about spherical geometry later, but I really want to focus right now on taxicab geometry. So taxicab geometry is different than Euclidean geometry in the way that you move from one point to another. So in Euclidean geometry, you can move between 2 points in a straight line. In taxicab geometry, you can only move horizontally and vertically. So before we get into taxicab geometry, if I give you point A and I give you point B and I say connect points A and B, in Euclidean geometry, you would do this. You go, wee, and you would connect those points, and you can connect them diagonally. In taxicab geometry, you can only move horizontally and vertically. So if I wanted to get from point A to point B, I have 2 options, but essentially I would have to move this way and then this way, right? Or I could have moved up first and then over this way, okay? When you think of taxicab geometry, what I want you to think about is that you are a bird flying over a city, or you're in an airplane flying over the city, and you are watching a taxicab drive along the streets. When you are in a car, you have to follow the streets, and essentially streets are horizontal and vertical. Yes, you have some diagonal streets, but we're not going to focus on that, okay? You can only move across the streets. You can't like drive a car diagonally across like a park, okay? So that is the main difference between taxicab geometry and Euclidean geometry. You have to move horizontally and vertically in Euclidean geometry, okay? So first thing I want to do is remind you that we can find the distance between 2 points in Euclidean geometry using either the distance formula or the Pythagorean theorem. I'm going to use the Pythagorean theorem because that's what I like to do. So I'm just going to find the regular Euclidean distance. From -1 to 4, that is a distance of 5. From 5 to 2, that is a distance of 3. So in Euclidean geometry, I'm going to take those 2 distances, square them, and that's going to get me my distance squared. This is 25 plus 9, which is 34. And then, oops, what am I doing? That's going to equal c squared. This is going to be 34 equals c squared, and then you square root it, and you can't actually square root it. So the Euclidean distance from points A to B is going to be the square root of 34. Now what I want to do is find the taxicab distance between those 2 points. So negative 1, 5 is here. That's point A. And then B is at 1, 2, 3, 4, 1, 2. There's point B, okay? This right here, connecting points A and B, should get me the distance of the square root of 34. However, I can't do that, okay? In taxicab geometry, I have to follow the horizontal and vertical lines. I'm going to do this in a bunch of different ways. First way I'm going to do it is go down 1, 2, 3, and then go over 4, 5, 6, 7, 8. So from A to B, in my red distance is 8. Now I'm going to try to do a different way, but I'm still only going to move horizontally and vertically. 1, 2, 3, 4, 5, 6, 7, 8. In the orange color, I was still moving 8. Let's try another way. Let's try green. 1, 2, 3, 4, 5, 6, 7, 8. I'm still going a distance of 8. Let's try this way. 1, 2, 3, 4, 5, 6, 7, 8. I'm traveling a distance of 8. What if I do 1, 2, 3, 4, 5, 6, 7, 8? Hopefully you're seeing that no matter what, no matter how you choose to get from point A to point B, in taxicab geometry, the distance is always going to be the same. It's going to be 8, okay? So we're going to mark this as a distance of 8. Some students have said before, well, what if you go like this way and then down? Well, you're still trying to go the shortest distance. So you wouldn't go away from point B. That doesn't make sense. You're still going towards point B always. But no matter which quote unquote streets you take to get there, you're still only going to travel the same distance. And for us, that's going to be a distance of 8. Okay? Now, there is another way to do taxicab geometry without graphing it and finding that distance. Okay? What we're going to do is actually the same thing we do to start finding the Euclidean distance, which is finding the distance in your x's and then finding the distance in your y's. The distance in my x's was 5. The distance in my y's was 3. If you take these two distances and add them together without squaring them, you get your taxicab distance. So you don't have to graph them every time. So it says determine the taxicab distance between these 2 points without graphing. So what I'm going to do is I'm going to find the distance in my x's. That's going to be 8. Find the distance in my y's. That's going to be 5. And then you just take those two numbers together and you add them. And that's going to be your taxicab distance without graphing. And that, my friends, is taxicab geometry and systems of equations. Again, I'm going to actually have the completed version of the notes with numbers 3, 4, and 6 done in Canvas for you. But hopefully you learned some information from these notes today. If you have any other questions, please go see your teacher during their normally scheduled tutorial times, and I will see you in the next video. Bye.